C congruent modulo M and GCDCM equals 1. Now I can divide that C and get a connection between A and B. So there are some criteria, some conditions before you can divide two congruences. So it's a little different. The proof is simple. We know that we are given AC is related to BC, so I can get my equation 1. And I'm given that GCDCM is 1, so I can get another equation because I can use the GCD as a linear combination of C and M. Now I can manipulate these two equations. I want to get a connection between A and B, so I will eliminate C by manipulation and I will get an equation that looks something like that. You can do the math. When you do that, you will get that this is some integer here, so you will get A is connected to B and the proof. There is a connection between the remainder and the congruence relationship. It's given by this proposition. If A is connected to B through congruence modulo M, it says if and only if A and B have the same remainder when divided by M. So the remainder when you divide A by M and the remainder when you divide B by M have to be the same. Here is the proof. We can use division algorithm. Let's divide A by M and then we will have a Q1 and an R1 using the division algorithm. And let's divide B also by M and we'll have a Q2 and an R2. Our objective is to show that R1 must be equal to R2 because A and B are related. Since A and B are related, we have this equation here. So M must divide A minus B because A and B are related. Let's use our two equations we have. So M must divide, when I subtract A minus B, M must divide this expression. Now if these are multiple of M, this is already a multiple of M, that means M must also divide R1 minus R2. But this is not possible because we already know R1 and R2 are numbers smaller than M. So if I subtract R1 minus R2, the absolute value has to be smaller than M. So it cannot, R1 minus R2 cannot be a multiple of M unless it's 0. So that means R1 must be equal to R2. That's the only thing that can be divided by M. And therefore we have the relationship. So if A and B are related, then their remainders have to be the same. They must have the same remainders. That allows us to do a little example here. The question says to find the remainder when 3 to the 47 is divided by 7. Now 3 to the 47, if you plug it into the calculator, it's going to either burn your calculator or it's a huge number. But we can use modulo relationships and see what is connected to 3 to the 47. Now, using the division algorithm, 3 to the 47 must be equal to Q times 7 plus an R. This R is the remainder that we want to find. So that means if I bring it over, 7 will divide 3 to the 47 minus R. Because that 3 to the minus 7, 47 minus R is a multiple of 7. That means 3 to the 47 is connected to this R. So what we want to know is, okay, what's the number that 3 to the 47 is connected to? But we need to know that this number R has to be a number between 0 and 7 because it's the remainder. So let's try and find a number between 0 and 7 related to 3 to the power 47. Let's see what 3 to the 47 is related to. It's related to itself. So what we are trying to do is to use our rules to simplify this. 3 to the 47 is 3 to the 45 times 3 to the square. And I can use the congruence multiplications to get to that. And I can also see, the idea is to bring it down to smaller numbers. I know that 27 is related to 6. Because 27 minus 6 is 21. I know that 9 is related to 2 because 9 minus 2 is 7. I know that 2 to the 4, which is 16, is related to 2 as well because 16 minus 2 is 14. So I know these simpler things. So I want to write it in terms of these numbers because I know where these are related to. So I'm writing with 27 here, 27 to the 15, and this is 9. 27 is related to 6, so it's 6 to the 15, and 9 is related to 2. And I can break it down some more. 6 is 3 times 2, so 3 to the 15, 2 to the 15, so 2 to the 16. And then 3 to the 3 to the power 5, that's your 15, and this is your 16. 3 to the 3 is 27, and that's related to 6. So we have that. 2 to the 4 is 2, and therefore is 2. This is 2 to the power 4. We can continue to break this down. You can of course work it here because now you have smaller numbers. You can do it on the calculator if you like, but I'm going to break it down some more. 6 is 3 times 2, and 2 to the 4 is 2. And you continue to break down, and eventually you will get 5. So 3 to the 47 is related to 5. What we want to do is to bring it down to a number between 0 and 7, and therefore the remainder is 5. And that's what we have here. 3 to the 47 is related to 5, and that 5 happens to be the remainder here, because 3 to the 47 minus 5 gets divided by 7. That's your example. Lesson 4, and what we discussed in lesson 5. What we discussed today was solving linear Diophantine equations, that is equations of this form, ax plus by equals c, and when there are solutions, and if there are solutions, how to find them. So it's pretty straightforward. You have solutions if the greatest common divisor of a and b divides c, then we have solutions. So you need to find one solution, and then there is a formula to capture all the integer solutions for this equation. So you can solve any Diophantine equation. Then we looked at congruency. That's a connection between two integers. We say that the two integers a and b are connected, congruent modulo m, if m can divide the difference a minus b. If a minus b is a multiple of m, then we say that a and b are related. And we discussed several properties. We did the algebra of congruences, that is, we can add them, subtract them, multiply them. Division is a bit tricky, so pay attention to that. And then we can use these connections that's there between integers to do various examples. So I hope you enjoyed it, and as usual, this is Dr. D signing off. Keep it simple, enjoy mathematics, and I'll see you next time. Bye for now.